In the last video, we discussed adiabatic work operations, which are operations that we can do to a single simple system that change some of its internal energy and work parameters without changing its entropy. In this video, we're going to introduce join operations, which take two or possibly more simple systems from our broader compound system and join them in a way that allows them to interact. So just to recall from several videos ago, what we have is a larger, oops, is our total state space gamma, which might be composed of multiple different state spaces. I'll represent that by this kind of blobby shape here. Now, suppose that we have some way of choosing a subset of this space. So maybe we take this subset. And I'll call this space kappa. Now, the result of a join operation that's specific to the subset kappa is that we end up in the state which maximizes the entropy on kappa. So this new state is the state on kappa with maximum entropy. Now, this definition is all well and good, but there's a bunch that it doesn't tell us. First of all, how do we choose a subset kappa of our bigger space gamma? Second, what does this have to do with sort of manipulating boxes of gas, which is our sort of paradigmatic way of thinking about what we're doing in classical thermodynamics? And the answer, I think, will become clear as we introduce some examples. So let's first talk about the thermal join, our first possible example. And what I'm going to do is I'm going to say that we have one compound system, which is composed of two simple systems. And I'll say each of those is a gas system with internal energy work coordinates UVN. So we'll say that the parameters here are U1, V1, N1, U2, V2, N2. And let's do a little drawing. Great. What we're going to do is touch these two boxes together. And after we touch them together, we're going to say that the barrier between them keeps the particles from the one on the left away from the away from the particles in the box on the right, but in such a way that they share kinetic energy. So they're bumping into this wall between them, and that wall is allowing kinetic energy to pass through. Perhaps the wall moves slightly in a way that bumps into the particles on the other side. So after the join, we know that the volumes of the two boxes should stay the same, and the numbers of particles in each box should also stay the same. But the energy may redistribute between the two boxes. So what is our subspace kappa in this case? So for the thermal join, we have, and we should point out that this starting state is important for kappa. But in any case, for the thermal join, kappa is going to be the set of all U1, V1, N1, and let me actually say these are primed, which I'll take to mean the possible values of these parameters after the join operation, U2 prime, V2 prime, N2 prime, such that, well, V1 prime is equal to V1, V2 prime is equal to V2, N1 prime is equal to N1, n2 prime is equal to n2. And then the only other constraint that we have is that the total energy of the system should not become greater or smaller. So what we'll then have is that u1 prime plus u2 prime is equal to u1 plus u2. So this is a well-defined subset of our total space gamma. Wonderful. And notice again that it depends on our initial starting state. So now, as a result of the thermal join, these two will share will share energy until they maximize the entropy on this subset. So let's figure out what happens in that case. Okay, now that we have our subset kappa, it's time to do our maximization problem. There are quite a lot of ways that we could go about trying to do this, but let's just assume that the entropies are all differentiable in order that we can use some calculus to basically help ourselves out. So to state the maximization problem, we want to maximize the entropy of u1 prime, u2 prime, but I'll write that as u total minus u1 prime, where u total is our u1 plus u2 from before we did the join. Then we can say v1 n1, v2 n2, since v1, n1, v2, and n2 are all constant on kappa. Wonderful. So we want to maximize this. Now I could have stated this as a maximization problem with constraint, but I've basically just put the constraint in right here. All right, good. So now how would we do a maximization problem like this? Well, in the way that we've now written it, we have exactly one variable. This is really just all a function, really a composition of functions, but becomes a function of the single variable u1 prime. And we can always handle maximization problems for functions of single variables with just ordinary differential calculus. So what we're going to do is we'll take, I'm still going to write this using partial derivatives, but that's just for, I suppose, notational convenience. So we'll take partial s, partial u1 prime, and set that equal to 0. Okay, well, this might be somewhat helpful because it gives us a way to sort of start thinking about this, but we don't know what form S exactly has. In order to make this in order to make this more meaningful, let's remember that S breaks into a sum of entropies on the different simple systems in the problem. So this implies, because the derivative operator is linear, that partial S1 partial u1 prime plus partial s2 partial u1 prime is equal to 0. But now let's rewrite this last equation here in a way that makes u1 prime a function of u2 prime. So all of this implies that u1 prime is equal to u total minus u2 prime. Good. So now if I want to take derivatives with respect to u1 prime, I can use the chain rule to do it. And actually, I'm realizing, sorry, I should have flipped these around, and this should be u2 prime as a function of u1 prime for a reason that will become clear in just a moment. So I'm going to take this second term and decompose it using the chain rule. So this will be partial s2 partial u2 prime times partial u2 prime partial u1 prime. All right, good. But then looking at this equation right here, partial u2 prime partial u1 prime is simply equal to minus 1, because this is a linear function and the coefficient of u1 prime is negative 1. So this all implies the equation ds1 du1 prime is equal to ds2 du2 prime. After I apply that minus sign and then move ds2 du2 prime to the other side. All right, so there is something that will become equal exactly when we're at the point that we reach after our thermal join operation. What sort of thing is this that we're using to characterize this partial of the entropy of one system with respect to its internal energy coordinate? It makes sense that we might want to give this value a name, and so we will. So let me do, this is in fact a definition. The temperature of a simple system is given by 1 over capital T is equal to ds du. Where now I've gotten rid of the primes and the subscripts because we're just talking about a single simple system. And maybe I should say the temperature T. All right, so now we have a reason to think about this quantity and define it. And it turns out that that quantity is temperature. Now, I'll leave it for you to check this, but it's good to make sure that this kind of temperature that we've defined here meets with our intuition of temperature. So one thing that we talked about way back at the beginning of the course is that we intuit that when we touch a high temperature thing with a low temperature thing, the high temperature thing will lose some temperature and the low temperature thing will gain some temperature. The hotter thing becomes colder and the colder thing becomes hotter. And it's a good idea to check that that is in fact exactly what happens when we apply this condition after taking the thermal join. Effectively, we're doing exactly what we would be doing if we took a hot system and put it into thermal contact with a cold system. Good. Now let me clean up the board and we can talk about one more type of join that's relevant for us to do some simple problems. Okay, now let's talk about the other kind of join that concerns us here, the mechanical join. All right, so what is the situation here? Well, the first thing that we need to do is figure out our subset kappa. And to do that, let's sort of take some motivation by looking at what's physically going on in a mechanical join. So in this case, excuse me, in this case, we're taking two boxes of gas, we're sticking them together, and allowing them to share some quantity. In this case, we have a sort of a difficult question to answer, which is it possible for them to share quantities without also sharing energy? The simplest way to get around this actually is to just state that these boxes start at the same temperature. So we'll allow them to share energy, but we'll find that it doesn't really matter. So, all right, there we go. So as stated, these boxes are allowed to share energy, but they're also allowed to move this partition between them. So this partition can move left or right. And the way that it will do that is that the gas in each side will push on the partition, and whichever one is pushing harder will end up pushing it to one side or the other. And it will reach some point of equilibrium after we allow it to move. Wonderful. So now let's figure out our mechanical join. So kappa, in this case, will again be the set of U1, V1, N1, U2, V2, N2, and all of those should have been primed. Sorry about that. Such that, well, we know that the numbers don't change on either side, so we can say that immediately. N1 prime is equal to N1, N2 prime is equal to N2. But we also have that U1 prime plus U2 prime is equal to U1 plus U2, and V1 prime plus V2 prime is equal to V1 plus V2. So in this case, the total volume, again, will be conserved, whereas the individual volumes of the two boxes will not be conserved. So we're going to do a very similar computation to what we did before, except that now both U1 and V1, both U1 prime and V1 prime could in principle change. So again, we're going to say that we want to maximize S of U1 prime, U total minus U1 prime. Then we'll have V1 prime, N1, V total minus V1 prime for V2, and N2. Excellent. That means that we'll have two distinct differential conditions. So the first one will be partial S, partial U1 prime is equal to 0. And the second will be partial S, partial V1 prime is equal to 0. Let's knock out the energy condition first, because we'll see that it's not very different from what we've already done. So we'll have D1 partial S1 partial U1 prime plus partial S2 partial U1 prime is equal to 0. But that's precisely the condition that we found before, right? So we will have D partial S1 partial U1 prime is equal to partial S2 partial U2 prime. But each of those is equal to 1 over the temperature. And we said that the temperatures were equal by supposition. So these are both 1 over T. And that implies that U1 and U2 will in fact not change in this particular example. And it means that we can keep this in mind in order to use this temperature to analyze the rest of the problem. Okay, so that's this condition. Now let's do this condition. Here we'll have partial S1 partial V1 prime plus partial S2 partial V1 prime is equal to 0. And this will lead us to exactly the same place as before by exactly the same chain rule argument. So we'll get partial S1 partial V1 prime is equal to partial S2 partial V2 prime. Now, it might seem like it makes sense to give this quantity a definition as well, and in fact, we do. This is going to be equal to the pressure divided by the temperature. Again, this is well defined because we know that these systems have the same temperature by our earlier supposition. So we'll say, by definition, the pressure P of a system is given by T times the derivative of its entropy with respect to V, where again I've removed all subscripts and things of that nature because we're only talking about a single simple system in this case, just like we were with temperature. All right, and with that, we've covered, I think, the really basic cases of joins. And we're almost done covering everything I want to talk about control operations before we hop into some more advanced and maybe interesting material. I'll see you in the next video.